So, now that we've figured out the difference between specular and diffuse reflection, let's use specular reflection and what we know about it to study and build a model of optical devices. We're going to use the things we knew so far with lenses and use them to build a model for mirrors. So, for lenses, we know that refraction causes light to bend as it changes into a new medium, whether it's going from air to glass or air to plastic. And as a result, since the light actually goes through the medium, your object that you're observing and your lens are going to be on opposite sides of the observer, right? But a mirror is different. A mirror uses reflection, and reflection bends light as it hits a new medium. And we're going to assume for now that when I say reflection, we're talking about specular reflection, reflection off a smooth surface, right? So a mirror uses reflection to bend light as it hits this smooth surface. But since it reflects back off the surface of the mirror, both the object and observer are on the same side of the device as each other. So what do they have in common then? Imagine I've drawn a giant Venn diagram with lenses on one side and mirrors on the other side, and here's the things they have in common. Both lenses and mirrors obey the lens maker's equation. So all that mathematical work that we did on Friday, it's going to be exactly the same for mirrors as it is for lenses. So, good. It also has the same pattern of image formation. So converging lenses had a positive focal length, and it could make a variety of images depending on where the object is with respect to the lens. Well, that'll stay true for converging mirrors, which is kind of nice. For a converging mirror that's far from the object you're looking at, you'd see a small real inverted image. And if it gets too close, you'd see a virtual upright larger image. Depending on where the object is with respect to the mirror, you get different images. It even keeps the pattern where diverging images have negative focal lengths and always make the same image no matter where you put the mirror. So if I put a mirror here, no matter where I put my object, the image formed in a diverging mirror stays the same type. Okay? So we're going to be able to classify images in the same way that we did with lenses. So just to review, we classify images by orientation, so that's upright or inverted. We classify images by their magnification, whether they're larger, smaller, or the same size as the image, or as the object. And keep in mind, if you missed a definition for magnification, the definition is the ratio of the size of the image to the size of the object. In this case, the size of the image cat is larger than the size of the object, so I expect some number greater than 1. If this cat is twice as big as the original, this would have a magnification of +2. And positive in this case because positive means your image is upright. If it were -2, it would be an upside down, twice as large cat. So we classify images by their orientation, their magnification, and whether they're real or virtual. And just like before, a real image is one that can be projected onto a screen, or in the case of this poor guy, projected onto his face right there. It's a real image because the light rays physically meet to form that image. And since the light and image exist in real life, it can get projected onto a screen. These are going to go for any converging mirror or converging lens, can make a real image. I included projector in there because that's the most common use of these converging real images. But there's many more. We'll get to the uses later. Whereas, another real image there that's formed by lenses we've talked about. Whereas virtual images do not meet up in real life. That image only occurs in your brain because as your eye sees the diverging rays of light, it assumes that light has traveled in a straight line. So they must have originated from some common location back behind the surface of the mirror. And since those light rays don't actually meet up, I can't project it onto a wall. Now, flat mirrors make virtual images. A quick check for virtual images is if you see an upright image, it's virtual. So a flat plane mirror makes a virtual image, and check this at your house, especially if you have a small mirror. If you have a small mirror and you look at yourself, you can turn the mirror slightly, and I don't see an image of my face show up on this wall. There's nothing I can do rotating this mirror around to put my face onto that wall, right? That's because the image formed in a flat mirror is virtual. So before we get on to like the curved mirrors, let's just do the flat mirror images first. So in your notebook, we've compared and contrasted lenses and mirrors. We've reviewed how the images are classified as real and virtual, upright, inverted, larger, smaller, same size. Now let's add on one more section about the images formed in a flat mirror. The images formed in a flat mirror are always virtual, upright, and the same size as you. So let's say I take this person right here. They're standing in front of the mirror, and when they do so, light from their feet hits the mirror, obeys the law of reflection, and gets reflected into the eye. Light from the top of the head hits the mirror, obeys the law of reflection, and our brain would see these two red rays and think, wow, they must have come from some source, because our brain thinks light rays have always traveled in a straight line. It must be from back here. That makes sense. So we see this virtual image of ourselves that's behind the mirror, where no real light is. If I had a mirror on the wall behind me, there's no light behind the mirror. That's not how that works. So always virtual, always upright, magnification equals 1, and equidistant from the mirror. So if I'm standing 1 foot in front of the mirror, my image is 1 foot behind the mirror. In a flat mirror, this equidistant principle means that my original object, ABC, when reflected over the y-axis, causes an inversion. Notice how I can't take triangle ABC and rotate it in any way to form triangle A prime, B prime, C prime. So one last visualization before we moved on to curved mirrors is that because of the law of reflection, this teapot always looks like equidistant to the object. Because of the law of reflection, if the object, let's say the teapot, is moved farther up, the image looks like it's farther behind the mirror. Right? So let's get on with a little bit of a break here, check our comprehension, and then we'll move on to curved mirrors.